This is an introduction to a structural optimization. So I call it a practical introduction to this particular topic because coming from industry with close to 2 decades of experience, if there is something that is lacking in the information that is available in the internet, it is the practical application of optimization that is missing. So what I would like to cover is I would like to cover that in my presentation today. So without much further ado, I'll start the presentation straight away. So here is the contents of this presentation today. So I'm going to give you first an introduction to general optimization with a very simple example. And also we are going to kind of just get into the introduction to the structural optimization. So what is actually the optimization from structural point of view. Then I will go into the topic of what is the difference between analysis and optimization, because many people are aware of the analysis approaches, whether it is finite element or classical hand calculation analysis approaches. But I'll highlight what are the differences between the two, again, taking a simple example. Then we'll move on to what is the role of optimization in the product development, and what are the key challenges, and we'll talk about them. Then we'll describe various types of optimization in terms of general optimization techniques that are available. Then I'll give you an example of, or go through the particular topic of optimization using the Altair tool OPTISTRUCT. So within OPTISTRUCT, what are how the optimization process is to be carried out. Then at the end, we'll move on to the conclusions, and we'll take any questions that you may have. So first, I'll give you an introduction to the process of optimization. So here is a definition of what is an optimization is. So optimization is the action of making the best and most effective use of situation or resources from all available and feasible solutions. So it is basically from, we can call it as a mathematical technique for finding an optimum value of a function out of several variables that are available. But the important thing is when those variables and the function is itself subjected to a set of constraints. So these are the 3 steps of the process. So first of all, we need to define the objective, or kind of what is the value of the function that we are trying to optimize. And we need to identify all the variables that are associated with it. And we need to define the constraints or understand the constraints. So in the design world, when we talk about structural design or structural optimization, so that optimization can be defined as a process which results in an optimum design. So what do you mean by optimum? So optimum is the kind of the best result obtainable under specific conditions. So again, we'll go through an example as to what we mean by specific conditions. And the most important thing is optimization methods are all applicable to kind of all problems where there is an alternative solution available. What it means is that, for example, if you take a problem and if there is only one solution, then obviously there is not much an optimization that you can do. Again, we'll come back to this particular topic when we take an example where normal solution itself is an optimum solution. So here we take an example. So to demonstrate what an optimization is, here we can take a very simple example. Suppose you want to go to a shop and you want to buy apples, and you have these 3 choices. You can buy 1 apple at 20p, you can buy 6 apples at 100p, or you can buy bunch of 12 apples at 160p. So here there is a constraint in the sense that all have a shelf life of 7 days. So now the question is, what is optimum purchase? Here when we say optimum purchase, so here we need to understand what is our objective. Obviously the objective is I want to pay the lowest possible money. And in this case, we can say that is the lowest cost per apple. So here it is a simple problem. So we can easily work out that option C is it results in the lowest cost per apple. That is why that would be the easy choice. But what if I introduce a constraint? So in this case, the constraint is that you can eat only 1 apple a day. Because all the apples have got only shelf life of 7 days, you can only eat 1 apple a day. So after 7 days, the remaining are going to go waste. So in this circumstance, by defining the constraint, the optimum purchase is going to be different. So obviously, I need to buy 7 apples because I can only eat 7. So the optimum purchase in this case is going to be option B plus 1 apple from option A. So if I were to buy kind of 7 apples for 7 days, obviously, if I choose only option A, I'm going to spend 140p. Whereas option B plus A, I'll have 120p. Whereas option C, it's 160p. So by introducing a constraint, the optimum solution has changed. So that is the most important thing. So the solution of the optimization problem depends on defining the problem correctly along with the constraints based on the alternatives available. So you study all the options available here, and then you make the right choice, which is the optimum choice. So in this example, it is very simple that, yeah, that is an easy choice to make. But when it comes to a structural design, where there are so many variables, the problem can be not so simple. So to give further introduction to what an optimization is and where in general the terminology, the mathematical technique is used. So the optimization is kind of used in operations research to maximize or minimize an objective considering variables and constraints. I'm sure most of you would have studied the operations research topic in your college, and it may be boring depending upon your interest, but it is one of the very good technique where an optimum solution can be obtained by a mathematical approach. So it is an analytical approach to solve the problems. And what it does is it breaks down the problem into small components, which all can be represented by mathematical equations. And then you solve the equations to find the optimum solution. So again, we'll take an example here. So a company makes 2 products and each of them require 3 processes, a forging, machining, and an assembly line. And the cost and the products are given in this table below. And in each week, you can have kind of 32 hours of casting time, 28 hours of machining time, and 10 hours of assembly time available. And you can make 2 products, and each of these 2 products require as shown amount of time, and that is a cost, and that's the price. So basically, that is a revenue that you will generate from A. So in this case, what is a variable? The variable is the time. How do you split the time in making the 2 products, product A and product B? And what is objective here? The objective is to maximize the revenue. So if I were to make just one product, either A or B, obviously I may not be making the right choice there. But again, it depends on the problem, equation, and solving it. And so here are the constraints that we can write down in this particular problem. So here I want to maximize the revenue, which is 15 times A, the number of products that I make, and 20 times the number of products that I make in B. And what are the restrictions or the constraints here? Is that the forging time, the machining time, and the assembly time. So those are the 3 equations. Each of them all have to be less than the available time for the total machine itself. And obviously, both the variables can be greater than 0. So these are the mathematical equations that have been written to represent this problem. And an optimum solution can be found by solving this problem and making sure that the revenue is maximized. So this is an example of an optimization problem using a mathematical technique in operations research. And the structural optimization is not very different. The only thing is the variables, the processes, and the equations are all different. But the fundamental principle of the process remains the same. Now let us move on to the structural optimization. So what is a structural optimization? So what we can define it as, it is a process of defining a structure that meets the objective using all the available resources and making sure all the constraints are represented. Obviously, for a structure, what is the objective? The objective is to be, I want to minimize the weight, or maybe I want to minimize the deflection, or I want to minimize the cost, or in some cases, I want to maximize the stiffness. So that is the objective that you need to define for your structural problem. what are the resources and variables that are available? So the resources are obviously the materials, and the variables are dimensions, because you can vary the dimensions to choose or to define what the product is going to look like. And what are the constraints? The constraints are obviously the dimensional constraints and the manufacturing constraints, because you might come up with a very exquisite and very innovative product, but which may not be possible to be produced or manufactured. So there will be obviously some constraints on how you will manufacture them. And obviously, many a times what happens is these resources are expanded or kind of researched to further optimize the product. I'm sure many of you are very aware of the composite materials. So composite materials and the need for it is kind of in place of metallic materials is come about because of the better or superior material properties that they offer. And obviously, there are some new materials that people are developing or industry is developing to reduce the weight and cost, and also to improve the corrosion and durability performances, depending upon the applications of that particular product. So what we can say is that we can say that the design optimization in structural design is an application of operations research, so which we talked about in the previous slide, which is a branch of applied mathematics, to kind of engineering problem design. So let us take few examples of the structural optimization. So here is the first example that I wanted to talk about. Is a case of, I'm sure many of you have seen this one. So the aim of this structure is to just carry the lines, the power lines. So whatever the wind load and the weight of the cables has to be supported by this structure in all environments. And as you can see that a particular shape has been arrived at based on the people's knowledge and experience mainly, and also depending upon the materials that are available in making these type of structures. So that's a very good example of an optimized structure. Then here is a kind of a imaginary bike frame that came out or kind of proposed by somebody, that you could have the least weight of the bike frame in this optimized shape. The another example that I want to show here is a lug or a kind of a load carrying member there. So here the top one is the conventional machined lug, for example, whereas the bottom one is a kind of an optimized one where the load transfer from the lug to all the individual bolts is kind of directly connected, and all the material in between, which probably was not carrying much of the load in that sense, has been removed, and hence an optimum shape or optimum weight has been achieved by this process. Obviously, these type of products are not easy to produce, not easy to manufacture. So we don't see them much outside, and also the cost of manufacturing can be very high. But when there is a need for weight reduction, as we will see in the next slides, as to what is the importance of reducing the weight, these products can be in demand. And the last product that I just wanted to show here as an example is an aircraft structure. Again, this is not the structure that you see outside, or it is what the current aircrafts are designed to, but it is an imaginary topologically efficient structure that can be designed for an aircraft fuselage, wherein the load transfer is very effective and weight can be optimized. This picture was produced by Airbus a few years back as a concept that could be coming in the future, and it has not yet come to the market, but hopefully in the future we might see aircrafts like this if we are able to overcome the limitations that are offered by the manufacturing. So what is the importance of structural optimization? So why do we need to carry out structural optimization? So here is the table which shows comparative savings for a different type of transport vehicles. I'm sure many of you will be able to appreciate that kind of the lesser the weight of the car, for example, is better for us because you can carry more people as long as it has the same engine. So here is the relative cost going from a family car to truck. and then to civil aircraft and military, and then a space vehicle. For example, what is the benefit that you will get by saving 1 kilogram on the weight of the car? If that in a scale of in the scale shown here, if you were to save $3 per kilogram on a car, for example, then the same kilogram, if you were to save it on an aircraft, civil aircraft, then the savings could be hundreds of that, 100 times of that. Whereas in a space vehicle, where the cost of propulsion is very high, you could be saving 1,000 times of that, for example. So this table shows the importance of saving the structural weight and carrying the loads very effectively. We'll see this bit of more of this in the coming slide as well. Before we do that, so kind of I wanted to say, what is a challenge? Why is it? What are the challenges that we face in doing the structural optimization? So here is a rule of structural integrity. What it means is like a chain is as strong as its weakest link. I'm sure all of you can appreciate it. What it means is that if I have one weak link in the chain, it doesn't matter what the other strength of the other chains is, but the weakest link will determine the total load capability of that whole chain. So what is the challenge for structure? So our optimization process need to make sure that all the links have the same strength, and to put it in a different way, to make all the links no stronger than they need to be, because there is no point in improving strength of one chain and then if the other one is weaker. So if all the links have got the same strength, which is just above the margin that is required for all the failure modes, then your structural optimization has resulted in a very optimized product. And in this case of a link and a chain, it's probably easy to explain. But when you take a complicated structures and where there is lots of load paths, whether it is a car body or an aircraft structure, for example, where defining all the failure modes and ensuring that all of them are just greater than 0 is not an easy task to achieve. And what is the other challenge that we face in this structural optimization? It's obviously the cost. So here is an example or a variation of the fabrication cost and the material cost and the total cost compared to the weight of the product. For example, if I were to make kind of the weight is very high, then obviously the material that the cost of the material is going to be high for a high weight product, and probably the fabrication cost is not going to be much because I'm not removing that much of a material, or there is not much material mechanical processes involved such as machining, and hence the fabrication cost may be low. But if I were to make a very efficient product, as we have seen in the lug case earlier, the material is big, the amount of material that I need is less, but the fabrication cost is going to be very high. So again, I don't want to end up on this spectrum. So there is a balance between the two, between the material cost and the fabrication cost, and hence the total cost. So the optimum weight will need to be which balances the total cost that is required, including the material cost, fabrication cost, or any other costs associated throughout the product usage, for example. So that's the challenge that structural optimization will face when you actually define the product. So what is a need? Let us look at another example of what is a need for a structural optimization. So let us look at this aircraft, Boeing 737 MAX, where whose maximum takeoff weight is 75 ton, for example. But the weight of the structure on the system itself is 43 ton, which is greater than 57% of it. What it means is the efficiency of this aircraft is less than 43%, we can say so, because the amount of payload that it can carry is less than its total weight. So how can we do it? What is the need? So if the structural engineers were to do a better job of designing the structure, then what you can do is you can save the weight of the aircraft, whether it is structure, system, engine, or whatever it is contributing. You can call all as contributing to the total weight of the aircraft. Then the aircraft can carry higher payload, and at the same time, it can fly longer missions. So that's the advantage of, or the need for the structural optimization. And the same thing can be shown for an example in the automotive industry as well, where there are strict regulations that are coming in terms of emissions of the aircraft. So the emissions relate directly to the weight of the car. So there is a need to reduce the weight of the car. And what is the best way than doing a proper structural optimization in coming up with an ideal structures for these vehicles. Now let us move on to the topic of what is the difference between analysis and optimization. So I'm sure many of you are aware of the conventional analysis approach, whether it is, in this case, we'll take a finite element analysis, where if I want to do an analysis, all the inputs that are required is I need a geometry, I need a loading, what's the boundary conditions, and what are the material properties. Once I have given all these inputs, I can produce my output, which is nothing but stresses, displacement, or natural frequencies, or what are the failure modes. So that's the conventional analysis approach. What is an approach in the optimization? So in case of an optimization, what it requires is it requires a design space. I mean, what is it that we are trying to do? And what are the variables, dimensions, and material properties? And what is objective? So rather than analyzing a given problem, what we are going to do here in optimization is that we want to understand what is objective and understand variables on the design space, and then come up with a design recommendation. That optimization results in a design recommendation rather than giving a solution. So we can say that while the analysis leads to the solution, so it gives you the solution to a problem, whereas the optimization task leads to a solution, which means it is not the only solution, but there are multiple solutions available, and you need to make a recommendation of the optimum solution that you can provide. So further going ahead in the same topic of analysis versus optimization. So for example, if I have a plate with a hole, for example, and subjected to loading, an analyst will say, okay, I apply the loading and I can find out what are the stresses at the edge of the hole. That's a conventional analysis. Whereas an optimization approach will be, oh, if I know the loading direction, then I can decide the shape of the structure or the shape of the hole, to be precise in this case, so that the structure is efficient. So as shown in this picture, depending upon the loading, I can make the hole in such a way that the stress concentration at the edge of the hole is reduced. So that's the key difference between the analysis and optimization. So let us take an example now to demonstrate the difference between analysis and optimization again. So now I have a cable that I need to kind of, a new cable is laid out, and I want to attach it to the web panel using a bracket, for example. So what would an analyst do? So analyst might come and say, okay, tell me the location where you are drilling these holes, and I will tell you the stresses for all the applicable load cases. So that's the conventional analysis approach that an analyst probably will take. So he will say that, oh, I need the geometry, I need all the loads, and I will analyze it, and I'll tell you what the stresses are when you drill the holes. But what is an optimization approach? Optimization approach is, you can say that I will suggest you the best possible place to drill the holes by studying the load cases that are applicable to this particular web panel. So let's take these two cases. So if I know that the load is applied in that direction, then you have a choice of drilling the holes here, or in that factor, for example, anywhere around the hole. So what would an analysis do? Analysis would tell, okay, I'll apply, you drill the holes, you tell me where you are drilling the holes, and I'll analyze and tell you whether it is okay or not. But in optimization, if you do a study in advance before actually designing, you can make a recommendation saying that don't drill the holes in that way because you are increasing the stress concentration, but rather you drill the holes here so that your stress concentration is less in this particular case. And in addition to that, the optimization approach will also say that not only the position of the holes, but also the distance between the two holes has also is a variable which can be optimized so that the weight of the bracket and the weight of the stress here can be optimized in that case. What I mean by here is that if I were to go with smaller distance between the two holes, that might result in a less bracket weight because the bracket is smaller, but it increases the stress at the hole for whatever the stress concentration it is there. Whereas if I increase the hole distance, which means I'm not producing any stress concentration, but the bracket is need to be longer. So you're increasing the weight of the structure. So that kind of is the compromise or various variables that you study in making these decisions in the optimization process. Now let us look at an example, again another practical example of understanding structural optimization and what we term by design space. So let us take this example of tray table in an aircraft where I have a tray table and I want to design this bracket here. So the question is, okay, what is the length? Obviously, you want to know what are the loads that are applied there. So you go to the regulations and understand what are the requirements for that bracket to be taking. Then you have to define the problem. So in this case, for the optimization, what we do is we say that the distance between A to B can be termed as the design space. That is a design space where you want to design the bracket or the arm within that distance. And the width and the stowage requirements. So what is the width of that? And what are the stowage requirements? Because it is not going to be like this all the time. You need to be stowing this tray table for takeoff and landing. So what are the stowage requirements? How much of it can be coming out of this? And how much need to go inside? And what is the space here? So those are the constraints. And you have the variables, which is what material I am using for this and what are the thicknesses. And finally, what is an objective? So my objective will need to be, it should not be too flexible that it will be when I kind of, for example, put my hands on it, it should not deflect too much. And also the stresses on it should be low enough so that it has sufficient strength, both under static as well as the fatigue loadings. So that is an example of kind of various terms that are required for structural optimization. So what is a design space? What are the constraints? What are the variables? And what are the objectives? So this particular problem, for example, if the design space is different, but all of the parameters remain the same, then the solution can be different. What do I mean by that? What I mean by that is, if my design space, which is the distance between A and B, is not this much, for example, whereas if it is different, then I could end up with a slightly different product. So depending upon the design space and obviously other variables as well, your product design or recommendation will be different.